All right, welcome to chapter 22, about Faraday's law. This is chapter 22 in all right, we're going to talk about curly electric field. Now, curly electric field has a little bit different from our Coulomb electric field that we've talked about so far. So let's talk about Coulomb's electric field. So for Coulomb's electric field, you have to have a charge, okay? And if that charge is positive, that electric field points away from the charge. And if that electric if the electric charge is negative, it points towards the charge. So how do we do curly electric fields? Well, we have to have a magnetic field. So let's say we have this blue disk with the magnetic field coming out of the page. And I'm concerned to find the curly electric field all around this dashed black line. So to do that, I have to, what I'm going to claim for this case is the curly electric field goes in a clockwise direction. So why is it a clockwise direction? Well, that's because the B field is increasing over time. So as time goes on, the B field keeps getting larger and larger. All right, so the trick to all of this curly electric field is finding the change in B. So this is the top view of the situation as we're looking down on it. And now I'm going to create a side view. So initially we had this magnetic field. Sometime later the magnetic field increased. So our change in magnetic field is up. So I have to add this delta B to my B0 to get B1. Alright, so I have my delta B. Now I can find my negative delta B. And then from that I can find my change in delta B with respect to time, and that's what we're looking for. So it points down, or I should say against, it points the opposite way of the initial B field. Alright, so how do you find the curly electric field? Well, you take your right hand and you point your thumb in the direction of minus B dt. So in this case, your thumb would point into the screen. And you see your fingers rotate around the direction of the electric field. Alright, that's how you find the direction of curly electric field. Or should I say, we get a non-Coulomb electric field by having a B field that changes in time. So let's look at another way of changing B field. Let's say I have the same blue area. This time my B field is still coming out of the page. I still want to find my curly electric field around this black dashed line. But in this case my B field is decreasing. It's getting smaller with time. So again, I have to find delta B. So there's my top view. And here comes my side view. So initially B0 is large, and then it decreases. So I have to add my dB to my B0 to get B1. And I need to find my negative B, which changes its direction. And so I can find my rate of change of B with respect to time and the negative of that. And so that points with the B field, the original B field. So you take your thumb and you point it out of the page. Your fingers curve in what direction around? Clockwise or counterclockwise? I hope you got counterclockwise. Let's try this one more time. But in this case, our original B field is pointing into the page. We are going to increase this B field. Okay, which way does delta B point? So I start off and my B is pointing down. It increases over time. Which way should delta B point? It's got to point down also. So my negative change in B has to point up. My rate of change in B has to point in the same direction as my negative change in B. And so it points the opposite direction of the B field. So you point your thumb in the opposite direction of the original B field. In this case, which way would that be pointing? Would it be into the page or would it be out of the page? It has to be out of the page. So my fingers go around counterclockwise. One more example of curly electric field. In this case, the B field is still pointing into the page. I'm going to decrease my B field now. Which way should my delta B point? Initially, it's large. I need to decrease it. Which way should delta B point? It's got to point opposite of my original B field. So my negative change in B has to point with my original B field. And so my rate of change of B field, negative rate of change of B field, has to point with the same direction as my original B field. Which way should my thumb point? Into the page or out of the page? It has to point into the page. So, which way does the curly electric field go around? Clockwise or counterclockwise? It's clockwise this time. Okay, I hope you're getting a better understanding of how to find the direction of curly B fields, because we're going to need to do this to apply Faraday's law. We're also going to need to understand magnetic flux. So it's just like electric flux, except it deals with B field, not the electric field. So, same idea. I have some area, and in this case the area is going to be the top of my disk here. So my normal always points out. And then if I have a B field, it can actually point in any direction. So in this case, I have it pointing, it has a component that's parallel to the normal and a component that's perpendicular to the normal. So if it's if the flux is out of the page, it's positive. So in order for it to do that, both a component of the B has to be parallel to the normal, and if it's going into the area, B has to be pointing in the opposite direction, or component of the B has to be pointing in the opposite direction of the normal. And then we count this the same way you do your dot product. You could have an angle, like I have in my picture here, that's going to come into the dot product. And how is the B field dot n changing as we move across the area? In this case, it's not changing at all. It's constant. We can factor it out front, and we just get the area. So, what is Faraday's law? Well, Faraday's law says you can produce an EMF with the negative change in the magnetic flux over time. That's what it says. Well, what is magnetic flux? It is that expression we just talked about. Well, we've talked about EMF before. EMF is what? EMF, I should say. We need to talk about how the magnetic flux can change over time. So several things can change. The B field, the strength and direction of the B field could change in time. The normal to the area can be changing in time also. And even the area could change in time. So when you take the derivative with respect to time, you have to ask yourself, what is changing with the magnetic flux? Is it the strength of my B field? Is it the angle between the B field and the normal? Is it the area in which we're looking at? Is it changing? So you have to ask these questions. Of course, if a lot of these things are constant, then we're not going to have any change in flux. If B, N, and A are all constant, nothing's changing in time, so we're not going to have any change in the magnetic flux, so our EMF should be 0. But if one is changing, we will get a change in our magnetic flux. And so questions you want to ask yourself, is the magnetic flux increasing over time, or is it decreasing over time? So how do we get an EMF? Well, uh, in the past, we have found the EMF by taking the integral of the electric field over some path, over a closed path, and you get an EMF. Well, that EMF should be the non-Coulomb EMF. If that is correct, then that is equal to the negative rate of change of the magnetic flux over time. All right, so we've talked about Faraday's equation. And what we're going to do is bring several of these ideas together, and they all come together in what's called Maxwell's equations. So what is Maxwell's equations? Well, Maxwell's equations is Gauss's law. We've just talked about that. There's also a magnetic form of Gauss's law. But since no magnetic field cannot exist without having a north and south pole, any closed surface that we enclose a magnetic field, the flux has to be zero. So this tells us that we can have no magnetic monopoles. Then we have Faraday's law, which we just finished talking about. That's part of Maxwell's equation. And then also Ampere's law that we just finished talking about on last Thursday. So these are what are called Maxwell's equations. And from these four equations, I can describe, or we should be able to describe anything that's happening within electricity and magnetism. So how do we use these things? Well, here's an example problem. Let's say a bar magnet with its north pole towards the origin is moving to the right towards the origin. So like the picture shows in below. So okay, at this instant in time, what is the direction of the B field caused by the dipole? At the origin, we get that direction. All right, so let's move it closer. What is the B field now? Since the distance is smaller, our B field has to be larger. So we've just increased our B field over time. We have a changing magnetic field at the origin. So the next question is, what is the change in the B field between T1 and T2? And that's going to be delta B. Now that we have delta B, I can find the negative change, which points in the opposite direction, this direction. And that is my change in magnetic field over time. In this case, the magnetic field was changing in time. And then for our last problem is standing on the negative x-axis, looking back at the origin, is the pattern of the curly electric field clockwise or counterclockwise? So again, I point my thumb in the direction of the negative dB dt, and I'm going to get what direction? I'm going to get I'm going to see a counterclockwise rotation of curly electric field. How about another example of using Faraday's law? This is problem 13 in the textbook, and we have a north pole of a bar magnet points towards a thin circular coil of a thin circular coil of wire containing 40 turns. The magnet is moved away from the coil so that the flux through one turn inside the coil decreases by 0.3 Tesla per Tesla times square meters in 0.2 seconds. What is the average EMF in the coil during the time interval? And it says viewed from the right side, opposite the bar magnet, does the induced current run clockwise or counterclockwise? And explain briefly. So, to do this, I have to use Faraday's law. Now, Faraday's law is interesting. This negative sign kind of deals with the direction of the current, the induced current that should come in, or the direction of the curly electric field. But I can find my EMF by doing this. Well, I got to get my change in flux. Well, initially it was larger. So it's final minus initial. A smaller number minus a bigger number should give me a negative value, and it decreases by 0.3. It takes, oh, sorry, 0.2 seconds, not 2 seconds. So my answer is going to be off by a factor of 1/10. And we see a flux through all 40 of these turns, so you can multiply the EMF you get through one turn times 40, because we have 40 turns of wire over here. And it says 6 volts. I think what we're going to get is 0.6 volts. Okay. How do we figure out the direction of the curly field? Well, initially the magnet is close. So the B field that is pointing through our circular loop here, our flux, is large. And sometimes later it gets smaller. So the change in B is that it points with the velocity of the bar magnet. And I want the negative change in that with respect to time. So that's pointing with the B field. And again, if I point my thumb in that direction, my fingers curl around the wire as pointed by my arrows for these non-Coulomb electric field. So in this case, I would see a counterclockwise direction. And this is I've just explained briefly how you get this answer. All right, one last one, a little more complicated of one though. So in this case, we have a toroid here that has a rectangular cross section where the inner radius is 9 centimeters and the outer radius is 12 centimeters. And the height of it is 5 centimeters, and is wrapped around by many densely packed turns of current-carrying wire. The direction of the magnetic field inside the windings is shown. On the diagram, there is essentially no magnetic field outside the windings. A wire is connected to a sensitive ammeter as shown. The resistance of the wire is 0.14 ohms. The current in the windings of the toroid is varied so that the magnetic field of the windings averages over the cross-section varies with time as shown. So at t equals 3 seconds, it increases to 1.6 Tesla at t equals 5 seconds. Then it stays constant for a period of time. And then at 12 seconds, it decreases until it gets down to 20 seconds and we have 0 magnetic field. It says make a careful graph of the ammeter reading, including the signs as a function of time. Label your graph and explain the numerical aspects of the graph, including signs. So, got to use Faraday's law. How is my flux changing? Well, I have some B field going through an area. What's actually changing? Well, the B field's changing. My area is staying the same. So let's find, okay, so we are interested in the first change in B field from 3 seconds to 5 seconds. So the B field goes from the final B field is 1.6, the initial one is 0, it takes 2 seconds. And the area is 0.03 centimeters to 0.05 centimeters. 12 minus 9 is 3 centimeters. So that should get us our EMF. And if we calculate that, I get a negative 1.2 millivolts. So how do we get our direction of our curly electric field in our wire? Well, according to this rectangle, the B field points into it based on this picture, or if you're looking at the loops of wire that go attach into the ammeter, they're looped this way like the square. And what's happening, the B field starts out small and gets larger. So in order for it to do that, delta B has to also point into the page, and I want a negative dB dt, and that has to be out of the page. And as if I point my thumb in that direction, I get a curly electric field that goes this way around the wires. And so that's going to drive a current that goes into the plus side of the amp meter. And I can get the amount of current by taking the voltage divided by the resistance of the wire. And since the current goes in the plus side of the meter, I have a positive reading on the amp meter. So our current at I equals 3 seconds is going to jump to this value, and it's going to stay that time as long as the B field changes at that rate. So at t equals 5 seconds, it will still be that value. Now I'm going to move from the 5-second time period to the 12-second time period. So I need to find the rate in my change in my magnetic flux. So what's actually changing here? We already know our A doesn't change, but does my B change over this time? If we look at our graph, it does not. So what's the derivative of a constant? It is 0. So we have 0 EMF, which means we have 0 current. So our graph would at t equals 5 seconds would go from 0.857 milliamps down to 0, and would stay at 0 until 12 seconds. Now I'm going to look from the 12-second to the 20-second range here. Again, I have to find the change in my magnetic flux. And to do that, I got to ask what's changing. In this case, the area is still constant, but my B field changes. So I need to calculate that. Well, in this case, it starts out high and goes low. So it's final 0 minus its initial of 1.6 Tesla. And this takes 8 seconds. And we have the same cross-sectional area before. And for this one, I get a positive 0.3 millivolts. So if I calculate my current the same way I did before, I get this current. But what we have to do is calculate our direction for our current. And in this case, the B field's still pointing in, except it starts large and then gets smaller. So my dB has to point out of the page, and I take the reverse of that. That means it's into the page. So I point my thumb in that direction, and it curls around this way. So as I follow the current as it goes around the loop, I find that I get a current that goes in the negative end of the amp meter. And if it goes in the negative end of the amp meter, that I get a negative sign for my current. So at t equals 12 seconds, my current should go down to a negative 0.214 milliamps, and that should hold constant for 20 seconds. Sorry, until we get to 20 seconds, not hold constant for 20 seconds, until we get to 20 seconds. Well, I hope you have a better understanding of how to do Faraday's law. We'll do some more stuff in class, and I'll see you on Tuesday.